Hi, welcome to the statics tutorials. So in this example, we're going to look at how to determine a force that's directed along a line in 3 dimensions. So in this example, we have this eye bolt here at A that's secured to a wall or floor. We have an eye bolt here at B that's secured to a wall or floor. And then we have a rope that's going from A to B. We know that the tension in the rope is 100 newtons. So we want to be able to write that tension going from A to B as a Cartesian vector. Let's say that we have measurements at A, so that A sits at an x of 1 meter, a y of -1 meter, and a z of 2.0 meters. So it's over, back, and up from the origin. Let's say that B sits at 0.5 meters in x, 3 meters in y, and 2.5 meters in z. So again, starting at the origin, B is out a little bit, over quite a bit, and then up a little bit. So we can construct a position vector that's the displacement going from A to B, and it's always going to be destination minus the starting point. So our destination is B, and our starting point is A. That's why we labeled it R position. R is always for position vector. And then from A to B. So we're going to take the x at the B and subtract off the x at the starting location, the A. That's going to make our x component, so we'll multiply that by I. Then we'll take our y at the destination, YB, subtract off our YA at the start. That'll be our y component, so times J. And then we'll take our z at the final point B minus our z at the starting point A. That's our z component, so that'll be times the k unit vector. So let's plug in our numbers. So we'll have 0.5 minus 1 here for our I component. We'll have 3 minus a minus 1 for the j component. And then we'll have 2.5 minus 2 here for our k component. So it's going to be negative 0.5 I. 3 minus a minus 1 would be 3 plus 1, so 4 for j. And then 2.5 minus 2 would give us a 0.5 for the k component. We need to get the magnitude of this position vector because we're going to need to use that in just a sec. So its magnitude is the x component squared plus the y component squared plus the z component squared. Add them all together and take a square root, and that gives us 4.062 meters. Now to create the tension, I used a T here, but you could use an F in here. To create the tension, we want to preserve all the direction information on this R vector, this position vector, but we have to resize it because the magnitude of this position vector right now is 4.062 meters. We need a vector that has a magnitude of 100 newtons. So what we're going to do is just divide it by the magnitude that it currently has, multiply it by the magnitude that it is going to have when it's a tension or a force vector. So that's going to scale this up. The other way to think about it is you could think about this as being a position vector divided by its magnitude, creating a unit vector, so a vector of length 1 that just has the direction but only has a magnitude of 1, and then multiply it by the magnitude that you want it to have. Okay? But either way of looking at it, when we plug in the numbers, we plug in the 100 for the magnitude of t, we plug in the r vector here, and then we plug in the magnitude of the r vector down here. And then doing this calculation, probably the easiest way to do is to do the 100 divided by the 4.062, and then just store that in your calculator's memory. And then you can multiply that number that you get by each of the 3 components. So it would be 100 divided by 4.062 times 0.5. That gives you the 12.3, and then carry the minus sign down. You have 100 divided by 4.062 times 4. That gives you the 98.5. 100 divided by 4.062 times the 0.5, and that gives you the 12.3 newtons. And so we're done. This is our final answer here. Just to show you that this actually worked though, we can check our vector and make for sure that its magnitude is correct. So we'll do our 12.3 squared plus our 98.5 squared plus our 12.3 squared, add them all together, take a square root, and sure enough we get that 100 newtons back. So our magnitude checks. The second thing that we would want to check would be, is the direction the same as the position vector? So we can calculate one of the coordinate direction angles for our position vector. Alpha would be the inverse cosine of the x component of our position vector divided by the magnitude of the position vector, and that gives us a 97.1 degree. Remember, when you're doing those coordinate direction angles, the positive and negative signs in here are important. And so you get the 97.1, and then doing the same thing over here, we take the negative 12.3 for our tension vector, divide by its magnitude of 100, do that inverse cosine, we get that exactly the same 97.1 degrees. I didn't do beta and gamma, but you could do those also to double check, and you would find that those angles would be the same. Thanks for watching.